is a new chapter. You have that in your book. Mathematical modeling of the dynamic system. So what is the mathematical modeling? Mathematical modeling, it is a set of equations, different types of equations, like differential equation, integral equation. Model means design. So mathematical modeling means you will design a system that will consist some equations, mathematical equations. Like this is a mathematical equation. You can model this. You can model this dy dx plus z. This is another equation. You can model that. You can model one system based on this equation. You can model this system based on another equation. So if you design a system based on mathematical equation, that is called mathematical modeling. Now, which type of system? Here we will talk about the dynamic system. Dynamic system. What is the dynamic system? Look, we have two types of systems. Two. One, static. Static system, the system does not change with time. That means this system does not change with time. Time means t. It just depends on the present input. The output depends on the present input. Like, if I just give an example of yt equal to xt. This is a static system because the output t depends on the input t. That is the present time. It is a static system. A static system does not change. Static means fixed. This is a static system. It fixed. It will not change. So I am changing my position. I am walking. I am not static. I am not fixed. I am walking. I am changing my position. My position changes over time. So this system we call it dynamic, changes with time. The system changes with time, that is called the dynamic system. Technically, how we can write it? The output depends on the present and past inputs. Present and past inputs. Let me give you an example. Yt is equal to xt plus xt minus 1. This is present time, present input. This is past input, t minus 1. This is a dynamic system. This is a static system. The system that only depends on the present input, we call it static system. And the system depends on present and past input, that we call the dynamic system. So practically, in the practical world, we don't have static system. All the systems are dynamic system. Suppose if you consider the weather, here, the temperature, the room temperature in this classroom, it is a dynamic, it changes over time. In the morning there is one temperature, now it is another temperature, in the evening there will be another temperature. It changes over time. Dynamic system. Everything, everywhere in the practical world, everything it is dynamic. It changes. It's not fixed. So this is why we will discuss the mathematical modeling of the dynamic system. That means the system that changes over time. It is changed. It is variable like this. So we will talk about this. We will design the system that is a dynamic system. We we will do the mathematical modeling, that is a dynamic system. So all the systems that we see, we design, that are dynamic system, not the static system. The static system does not exist in the practical world. Only mathematically you can do that. Mathematically, by writing mathematical equation, you can do that. So that's why the chapter name is the mathematical modeling of the dynamic system. So the system that we say to be dynamic if the output depends on present and past input. Suppose here there was two examples are given. One example is integrator, another one is differentiator. What are these? Integrator. This is the integrator, and this is differentiator. Changes over time. Integrator and differentiator. So integrator are having a limit. Suppose the limit is 0 to t. The limit. We always use the limit. It can be 0 to 1, 0 to 10, 0 to 100, anything. Whatever it is the limits. That means this function, whatever it is here, it depends on these values. That means present and past. This one changes over time. It is called rate of change. Rate of change for anything like x. Rate of change. So here also it depends, it is also a dynamic system. So integrator, differentiator, those are dynamic systems. These are some examples. We will talk about in more details about these examples. Like mathematically how we can write that. Suppose this what I actually wrote here, this one, the 0 to t, this one we can write in this way. This is called tau. We will use this term later on. So remember this is tau. Tau means time. Tau is a time constant. Time constant. So here it is a time, it is a function of tau. So this tau depends on the value of 0 to t. So that means 0 is the past value. Here it is the present values. So 0 to t. We can write this or we can write this in this way. And this is our input. U is the input, Y is the output. Here T is the time. One example, a moving mass. Suppose what happens if you apply a force to a mass or anything. Suppose this object having a mass M. So you apply a force. It goes. It will displace. It will change the position. While you apply a force, it will change the position. This position, the displacement, this is called x. This is the displacement. This is the displacement. We call it x. And if there are two positions like this here at the beginning, this is x1. Then after that it is x2. Then the difference we call it del x. Del x equal to x2 minus x1. Changing positions. If x1 is equal to 0, then we can directly write it x2 or x. Now Newton's second law tells us, Newton's second law, this is, we call it, if we apply the force, if you apply a force to an object, it is directly proportional to its acceleration, A. This is the second law, Newton's second law, you already know that. You studied that in school. If you apply force to a mass or to an object, the force will be directly proportional to its acceleration. What is this? This is acceleration, A. So you can write this F equal to ma. This m is the acceleration constant, that's the mass of this object. We already know that. So what is this A? A. What is this A? A we call it rate of change of velocity. dV/dt. Rate of change of velocity. And what is V? V is rate of change of time, displacement. Rate of change of displacement, X. This X. Rate of change of displacement. So together we can write this d squared x dt squared. Now this d squared x dt squared, shortly we write it in this way, x double dot. That's why here you have seen this x double dot. So I will write it here. Suppose if I just write dx dt, this one we will call it x dot d squared x dt squared. This one we will call x double dot. Shortly we write it, and we will use this term here everywhere in control system, because it takes long time to write this dx dt, d squared x dt squared. We also need to write a longer equation, very long equation. So we shortly write this way. So this is coming from the Newton's second law, and we get this F equal to mx. It's just an example in the for a mechanical system, in the dynamic system. So why do we study the system? How we study the system? When we study a system, we need a model. There are two types of model, whether it is a physical model, actual model. This is an actual model. This chair, this table, it is actual model. It is actually built. This classroom, it is an actual model. This one, it is an actual model. But not all the time you will find the actual model. So sometimes we design the model by using some software experiment. We experiment with the model of the system inside. Like by using method, we can design a model. So the physical model or experimental model too. And this experimental model can have two types: physical model or mathematical model. Now the physical model, in the experimental model, there can be a physical model or mathematical model. So here we are learning how to do this, not this physical model, because physical model is the final version of the mathematical model. Mathematical model is the primary model to design a system, because when you want to design a control system, first of all what you need to write down the equations, mathematical equations. You need to write down the mathematical modeling. Without mathematical modeling you cannot design any system. So you need to know that how to write a mathematical modeling, how to write the mathematical equation to design a system. So we have the mathematical modeling. So mathematical modeling can have two types. One, analytical solution. Like write down the equations and solve it. We will see that later on. We will solve the problems. So write down the equations and solve the problem. And then there will be another type like simulation. By using different softwares like MATLAB or other simulation software, you can design and you can simulate it directly without writing any equations. You can do that because there are many blocks are available in the software. Many blocks. You just connect all the blocks, take the block and connect it all the blocks and simulate it. You don't need to write the equations. So here we will learn this analytical solution, and here these two are having two different. We can analyze it in two domains. One in time domain, another one in frequency domain. So time domain is what actually we have seen that physical world what we have, those are the time domain. Time domain. But while we analyze the system, we cannot keep it in time domain. Time domain is not good to analyze the system. So we must need to convert it in another domain. Mostly we convert it in frequency domain. While we analyze in system, we find out the system in time domain, then we convert it in frequency domain. Then we analyze it. So here we need to analyze it in frequency domain. Frequency domain means this omega or f. Also there is another term, we can use it S. Here we will see S. All are in frequency domain, we use this. So omega, f, s, anything if you see in your equation, that is in frequency domain, not in time domain. Time domain you will see the function in t. And in frequency domain you will see omega, f, s, anything. Anything it is in your equation, that is in frequency domain. So how we do this? How we convert this? We convert this time domain to the frequency domain by using Laplace transform. And we convert this frequency domain into time domain again by using inverse Laplace transform. We apply Laplace transform to convert time domain to frequency domain, and we apply inverse Laplace transform to convert frequency domain to time domain. So we will talk about that Laplace transform later on while we will solve the different types of equations. Now, this time domain and frequency domain, finding the solution in time domain and frequency domains are very important. And then we convert also in the mathematical model, we need both set of equations. So why do we need both set of equations in time and frequency domain? That we call hybrid domain. Hybrid means together at the same time in time domain and frequency domain, in both. Alright, so in the modeling, there are two types of modeling are available in control system. One is mathematical modeling, another one is state space modeling. We will not talk about the state space modeling here in this course. We will talk about the mathematical modeling only. Mathematical modeling, not the state space, because we have a short course, short duration of course, 6 weeks. So we will only consider the mathematical modeling here. So I already talked about this mathematical modeling. What are this? It is a set of mathematical equations, like differential equations. I already wrote you different types of equations. So mathematical modeling, it is a set of equations, and that will describe the input and output behavior of the system. Suppose I write this. This is the system. I have xt input. This is my input of the system, and I have yt, that will be our output of this system. And inside, this is my system. This system we call it ht. T. Now this is in time domain. Now, if I convert it in frequency domain by using Laplace transform, what I can write it? I will write it this way: xs. We use small x and greater x to differentiate both x. So it is we use a small x for the time domain. We use greater x for the frequency domain. Ys. And this will be hs. So s we use it for the frequency domain. So this is the time domain system, this is the frequency domain system. Now the mathematical modeling, we use it to get a relation, to analyze the relation of input output behavior of the system. So this hs, it is called transfer function. Transfer. So we can write this Hs is equal to Ys by Xs. Hs is equal to Ys by Xs. What is the Ys output in frequency domain? This one is input in frequency domain. In frequency domain, not in the time domain. So the mathematical model, we use it to analyze to find out the input and output behavior, the ratio of the output and input, and that is called the transfer function. And this is what we need to find out the stability of the system, to find out the behavior of the control system. So we will talk about it later on. So this equation is also very important. We will write it here. I will write it here. Hs equal to Ys by Xs. So this one we use it for time domain, and this one we use it for frequency domain. And how do we convert this? By using Laplace transform. And there are other transformations like Fourier transform we use to convert it from the time domain to frequency domain also. Fourier transform, Laplace transform. Those are quite common method to convert time domain to frequency domain. Here we are focusing on time Laplace transform here only. Now, why do we need to use them, or what is the uses of this model, different types of mathematical model? So we use this mathematical model for the simulation. After you write down the equations, you will simulate, find out the behavior, and then you simulate it by using different types of software. We use this mathematical model for the simulation. Second, prediction or forecasting. It is a very important. When you design a control system, mostly what the control system does, mostly it predicts the system. It will predict the output. It will predict the future output. It will forecast the future behavior. Suppose the temperature of this room. Now you are now here, but you can see that tomorrow, what will be the temperature of this room? Because there is a weather app in your mobile. You can check those and you can see the weather update. Tomorrow, what will be the weather of this room? This is the control system actually does. It will forecast the behavior of different systems. So prediction or forecasting, this is another term. It is characteristics. Third one, the diagnostics. Diagnostics. Mostly we use it for in the biomedical engineering, in the biomedical sector, in the medical. There are different types of medical tools are available. MRI, CT, ECG. In the medical, there are different types of diagnosis are available. In the diagnosis, there are different types of control systems are available. We need to use the control system to diagnose our body, to find out the disease in our body. Same thing happens in the prognostics. Prognostics means if you have any problem in your smartphone, electronic devices, any electronic devices, if there is any problem in the electronic device, you need to solve this problem. That is actually we call the prognostics. The last one is the design and performance evaluation. Performance, a very important tool of the control system. While you design a system, we want a very high performance of my system. So how do we find this performance? We find out the performance by finding the gain. This, what actually called the transfer function, there is another term, another name that is called gain. So here, this is called the transfer function. Also, we call it gain. Gain. What is the gain? Output by input, the ratio of output and input. the ratio of output and input, we call it the gain. So if you find out the output and whatever the input you know already, so you can evaluate the performance by finding the gain of that system. Any all the time. So whenever we design a system in the mathematical model or the simulation, always we find out the gain all the time. We find out the input and output, and we find out the gain by finding the transfer function. So that is another characteristics of the mathematical model, why we use the mathematical model. The last one, control system design. So to design a control system, this is the first tool, first step. Mathematical modeling is the first step to design a system. First of all, you need to write down the equations, then you can design a system, otherwise you cannot. Now there are different types of systems are available. Here you are the mechanical students, so we will focus on mechanical systems. We will not talk about the electrical systems here. There are mechanical systems. So we will discuss the different types of mechanical systems. We will analyze different types of mechanical systems. So to analyze the mechanical system, there are three parts: translational mechanical system, rotational mechanical system, and the mechanical linkage. Translational and rotational, we will cover these two today. This one we will cover in the next class. So translational system and rotational system, what are these? Translational system, mostly we call it linear motion, straight motion. And rotational is the circular motion, circular, like the velocity of the car. It is rotational motion. So here there are two examples are given. Like the first, the translational, mostly we use it for linear motion. Linear means this, one direction, or this, straight or back. So there are different types of linear motions are available. Like there is an example. This example is very important. We will analyze this example later on. So here we have a plane. This is the plane. And with the plane there is a spring. This is the spring. And what is this? Mass. An object. And this one we call it damper. Remember these three words because we need to analyze this whole system based on these three. So there are three parts. First one, this is called spring. This one is the mass, and this is called damper. Now what happens? Apply a force. You apply a force here. Now while you apply a force, there is a spring. It will stretch. The spring will stretch, or the spring will change its position. That means there will be a displacement. So the displacement, mostly that one, the first one we call it the Newton's law. The Newton's law tells us that if you apply a force to a mass or to an object, there will be a displacement. And in our previous slide we have seen that F is equal to mx2 dot. In the linear motion, while you apply a force to a mass or to an object, what will happen? There will be a displacement, and that displacement we can define it by a field mx. We just see it in our previous slide. But there is a spring here now, and what it will do? It will provide some restoring force, because this spring, it will take back this. Because if you apply a force, it goes, and the spring will take it back. This is called restoring force. Restoring force. And this restoring force is directly proportional to its displacement. This restoring force is directly proportional to its displacement. Now apply force there, and this restoring force is acting in opposite direction. This one in this direction, this is in another direction, opposite direction. That's why we use this minus. Opposite direction. That's why we use minus. Now this one we call it, and we use a constant value. This is called a spring constant. I will talk about this later on, and we have a detailed discussion also based on that. This is just the basics. So remember this, there are two forces. Applying a force to a mass, and there will be a restoring force. So this is one force you apply, and there will be another force to restore it by the spring. So this force we call it F equal to minus kx, and this is M F equal to mx2 dot 2. So this is the linear motion, and there is another one. This is called the circular motion. Circular motion is this. Circular motion. These are the gear. These are the gears. Mechanical gears. Different gears. We will talk about the gears in the next class. Different types of gears are available. So we will talk about the gears. So because of the gear, it will rotate, and while it will rotate, there will be a force, and that force we call it tau. Tau. Here we will use tau, or some equation you will see t. T or tau. These are called the rotational force. Rotational force. And this is F. This is the linear force. Linear force we use it for F, and for the rotational force we use tau or T. While there is a rotational force, we will apply the rotational force. There will be a rotational displacement, and that one we call it theta. We will see it later on. Now let's talk about the first one, translational system. In the translational system, there are three parts, three main components. One, spring, mass, and damper. I already showed you that. Here, we have three components. This spring, we have another component, mass, and this is the damper. So here we have the spring, mass, and damper. For each one, there will be one force. We need to design, we need to do the mathematical model for each one. For each. So how can we do this? We will write down the mathematical equation for each of these parts. Now first one, it is the translational spring. The translational spring, mostly while here is a force, if you apply force to it, so here if you apply force here, apply force here, and while you apply force, and this will provide some displacement, suppose here, so it will be displaced. So this displacement we call it x or del x, because you are applying a force, the spring will displace, it will be displaced, and there will be a displacement, that is called the del x. I already showed you that equation. So what is actually happening here? If the mechanical element is deformed means what? Deformed means change its position, change its shape. Deformation means change its shape. Here, this is stretching. That means it is changing its shape. So it will be deformed by an external force F. So the deformation is directly proportional. This deformation is directly proportional. Proportional means alpha. So the deformation is called x. X is proportional to the force applied to it. F is proportional. X. This is x, not this is x. So the deformation is directly proportional to the force we apply to it. So we can write this F is proportional to x. And while this is F is proportional to x, so we can write this as Ax. We are not using minus here because why? Because we are applying the force here. It is not a restoring force. It is just we apply the force and it will deform. So it is not a restoring force. So it is just directly proportional to it. And K, what is this K? K is the spring constant. We have that here. Now, while F, if F is an applied force, and if we have a deformation from x1 to x2, x1 to x2, so this one we call it del x. So del x will be x1 minus x2. Look at this deformation. Apply a force and it will deform. Change its position. So we can write this F is proportional to del x here. So F is equal to K del x, and this is nothing but x1 minus x2 here. This is the first one for the spring. This is the force you apply the spring and the equation. This is the mathematical equation. This is the mathematical model for the spring. So this system, so you can see this is a small system. That is a small mechanical system, and this is your mathematical model. This is your mathematical model. For this system. So any system you can convert it in mathematical model, in mathematical equation. That system we convert it in mathematical equation, mathematical model. So you need to write down equations in this way for any system. Like this system, you can write down mathematical model. For this system, you can write down the mathematical model. For any system, you can write down the mathematical model. So the K is the spring constant. For any system, you can here this is the spring. That's why we are using K. K is the spring constant and expressed in Newton per meter. This is the first one. Now let's talk about the second one. This is the first one what we have seen for the spring. Now we will talk about the mass, translational mass, linear mass. So translational mass is an inertia element. Inertia means what? Inertia means it is coming from the Newton's first law. Newton's first law tells us that if there is no force is applied, the static object will remain static all the time. So inertia means it will stay fixed. It will be stable all the time if no force or no external force is applied. So now here, this is an object. This is an object. Here, this object. And all the objects are having mass. You will not find any object without mass. So no object without mass does not exist. In any system, in the mechanical system, even in electron, and electron are having mass. Proton are having mass. Proton, electron. So all the objects are having mass. In a practical world, you will not find any object that does not have any mass. So all the objects are having mass. So now, if we are considering an object, now apply a force. Apply a force, and because of that force, there will be a displacement. There will be a displacement del x or x. And we already know about this Newton's law, Newton's second law, that if we apply a force, there will be a displacement, and that displacement we can write it is proportional to A. I just showed you that before. I'm not explaining it again. So this one we write it F equal to MA, and which is F equal to Mx double dot. Mx double dot. I already explained to you before, so it is like just like that. Because we have d square x dt square, we can write it x double dot. And that displacement is given by the Newton's second law. This is the Newton's second law. This is the second one. Now, this is the third one. I didn't discuss it before. So, this is called the damper. Remember the name damper. This is the symbol of the damper. Now, we will talk about this. If the damping or viscosity or the friction, if we consider, we always need to consider that, because in a plane, this plane, this is the plane, this is the plane. I am walking, that means there will be friction. Everywhere there is a friction. No plane are having friction less. So all the plane are having frictions. When you there is a velocity, something is going on, there will be a friction. When I am walking, there is a friction all the time. So because of that friction, there will be a damping force. Damping force. So that's why we need to use some damper. So we call this symbol, it is a damper. Now, if we apply a force to a damper, again there will be a displacement. Whenever there will be a linear force, there will be a displacement. So, first of all, look at this one. I will explain it to you. Then you can understand the damper well. Alright, now look at this. Here there are two models. One model does not have any damper. Another model, I have a damper here. This is the damper. So in the first one, what is the oscillation? The oscillation, look at this. It oscillates constantly. And it will go on. It will go on like this. It will go on like this. But while we use the damper, look at this. It is decreasing, its oscillation decreasing, and it is going to be stable. Stable. And this is called steady state in a control system. Steady state or stable state. In a control system, we always want all the system is in this state. All the system in this state. If it is not in this state, then our system is not a good system. Our system, all the system that you use in your smartphone, all your tablets are in steady state, stable states. All the system, all the control system, good system are having steady state, stable state. So look at this. It is going to be stable, and that will make a stable system. But here it is oscillating all the time. It goes on to the infinity. It will not be stable. So why we are using damper? We are using damper to reduce the oscillation, to decrease the oscillation, and make our system stable. That's what we do by using damper. This is the mechanical system. In the electrical system also we need to know that we have. Let's take the break. Then we will